Most real devices and components are going to exhibit both resistive and reactive properties. Additionally, in an interconnected power network, thousands if not millions of devices interact electrically, and we have to really therefore consider the equivalent electrical behavior of capacitive devices, of inductive devices, of resistive devices, all connected together in different configurations. But how do we do that? What we have to consider is that although reactance and resistance are both measured in ohms, you can't add them together. You can't take 5 ohms of resistance and add it to 5 ohms of inductance and get 10 ohms. That's not how it works. Additionally, we saw that reactive properties of capacitors result from the electric field, and they tend to cancel out the reactive properties of the magnetic field properties of inductors. And so they tend to cancel. And so to address both of these issues, we have to use this new concept to us of a complex notation or complex numbers. A complex number is a number that contains a real part, which is an ordinary number corresponding to a measurable physical quantity, and containing an imaginary part, which kind of corresponds to oscillatory behavior. If you recall, we have what we call the imaginary unit, I. It's equal to the square root of -1. In electrical engineering, we've already used I to represent current, so in this case we're going to replace it with J. You'll see throughout your classes that electrical engineers use the number J to represent the imaginary unit, because I would be too easily confused with current. The complex plane that we're showing here is a graphical representation of complex numbers. On the complex plane, the x-axis here represents purely real numbers, so we call that the imaginary or the real axis along the x, and the y-axis represents purely imaginary numbers, so the y-axis or the vertical axis is called the imaginary axis. Complex numbers can lie anywhere on the complex plane, and what they represent is a combination of real and imaginary parts. The complex number C equals A plus JB refers to the point A units to the right of the origin and B units above, where A is the real part and we call B the imaginary part of C. For example, if we had the point C equals 4 plus J3, we could come out 4 units on the real axis. We could go up 3 units on the imaginary axis. We now have the point C equals 4 plus J3. 4 being the real part of that, J3 being the imaginary part of that. Often when we write complex numbers in this notation, C equals A plus JB. Some people like to write that as C equals X plus JY. We call that rectangular form. An alternative complex notation is to use polar form, in which the complex number is represented as a vector in terms of magnitude and direction. So if we want to represent this as this point as a vector, we draw a line extending from the origin to the point. The length of the arrow is the magnitude, so we will call that the magnitude of C, and it's usually denoted here with these pikes. Those 2 straight lines are called pike of C, and that just means magnitude. And then there's an angle, and that angle is formed between the arrow and the real axis. So as we specify that, we typically denote that as theta. And polar form, therefore we can write that same complex number as C is equal to the magnitude of C at an angle theta. And so there's equivalent C there. In a somewhat less common notation is the use of exponential form. Exponential form uses a mathematical identity, Euler's identity. We'll encounter this quite a bit in electrical engineering, but it's E to the J theta is equal to cosine theta plus J sine theta. So exponential form uses that, and we can express C in exponential form as C equals the magnitude of C e to the J theta, and that's because of the Euler identity there. We'll actually do some proofs of that later in the course. So therefore, complex numbers can be represented in 3 equivalent notations. They all look different, but they mean exactly the same thing. The first is rectangular form, where the complex number is represented in its real. and imaginary parts. A is the real part, B is the imaginary part. We can represent it in polar form where we have the magnitude and the angle. So magnitude of C at an angle of theta. And exponential form, which looks just like polar form. It's just kind of a different way to write polar form. Clearly, since they all are notations to indicate the same points, we have to be able to convert between the different forms. So first, let's figure out how to convert from rectangular to either polar or exponential. What we can do is if we had a point on the complex plane, this point here, A, B, remember this is the J plane, the imaginary plane, this is the real plane. Here we have C, technically the magnitude of C, and theta. So all we have to do is apply a little bit of high school geometry here, the Pythagorean Theorem. We know that the height of this triangle is A, the base of the triangle is B, what we call the hypotenuse of the triangle is C. Pythagorean Theorem says C squared equals A squared plus B squared. We take the square root of both sides, and we end up with the magnitude of the vector C is equal to the square root of A squared plus B squared. So to get if you know the real and the imaginary coordinates of a complex point, you can then determine the magnitude using the Pythagorean theorem, and then we can use a little bit of geometry, inverse tangent in this case. Theta is going to be calculated as arctan of what? Of B over A. And where does that come from? Well, tangent of theta is opposite over adjacent, so tan theta equals B divided by A, so we take the arctan. We can use that right triangle also to convert either polar or exponential form to rectangular form. So if we know C and we know theta and we want to calculate A and B, we can use the Pythagorean theorem again. A equals the magnitude of C times the cosine of theta. And B equals the magnitude of C times the sine of theta. These conversions can easily be employed but warrant one word of caution regarding the use of this inverse tangent. Really, they're not too hard to use. It's high school math, but we got to be careful with this tangent. Because the tangent function is periodic, two different angles can produce the same tangent function. Similar angles in the first and the third quadrant, first quadrant and third quadrant, and similar angles in the second and fourth quadrant will result in the same tangent function. And therefore, care has to be taken to ensure that the angle calculated by the inverse tangent function corresponds to the right quadrant. You've probably already seen this in calculus.